So welcome everyone to the first day of the SEBA and VOLTHA track at ONF Connect. Over this afternoon and tomorrow afternoon we'll be going through a number of presentations on various things related to SEBA and VOLTHA and all the things that it builds upon and around. So this talk is about SDN enabled broadband access, or what we call SEBA. But at various points in this talk I'll be highlighting other talks that we will see today as well as tomorrow. So keep an eye out for that, and if that particular topic interests you, I do encourage you to attend those talks. So I'll be covering a wide range of things and only scratching the surface in some of these things, but some of these highlights that I'll be pointing out will go much deeper into that particular topic. So let's start things off by talking about what we call CORD, or central office as a data center. Now as you know, telecom operators, cable operators, they have a lot of these locations very close to the end user, those end users being residential end users, mobile end users, as well as enterprise or business customers. And these locations are the first stop where this traffic hits, and it has evolved over the last 100 years in various different ways, such that traffic from residential subscribers goes through a set of equipment, but for the mobile subscribers goes through a completely different set of equipment, and so does the enterprise or business customers. So what has happened is that over the last 50 years there has been a lot of equipment, a lot of different kinds of managements, each equipment having its own management system and so on, and it has been very difficult to run these central offices. The idea behind CORD was that what if we could take these central offices and the traffic coming from these different subscribers, but putting them on the same set of commercial off-the-shelf equipment and white box switching hardware, right? Basically bring the ideas behind cloud, SDN and NFV to the central office to achieve the economies of a data center, but also the agility of a cloud provider. Okay, so that's the central idea behind CORD. Why am I talking about CORD? It's because SEBA is built on CORD, right? So if you look at the ONF set of projects that you will be hearing about over the next 3 days, ONF is involved in a number of different projects, all of them open source projects, and SEBA is one combination of these projects that I will be going into a little bit in more detail over this presentation. Okay, so it helps to look at what traditional residential access looks like, so you can understand how things have evolved when we disaggregate this equipment and then run it using software running on bare metal switching hardware, whether it's commercial off-the-shelf servers or white box switching hardware. Okay, so in a traditional residential access, typically now I'm looking at passive optical networks. That is a head-end box known as an optical line terminal that then goes through a fiber distribution network and reaches the homes, where you have an optical network unit, an ONU or an ONT that talks to the OLT, and behind that a residential gateway, and then other kinds of services behind it, voice, video, data, and so on, right? And a number of these OLTs then get aggregated into what is known as an Ethernet aggregation switch, and further then that traffic gets terminated at the BNG, or the broadband network gateway. So this is how traditional, this is the set of equipment that has been used for residential subscribers, or some variation of these. Okay, so what we do in CORD and in SEBA is that we say, okay, so let's take the OLT, but take the only part of the OLT that is meant for doing the optical work with the set of ONUs, take the MAC functionality out of the OLT, okay, leave that in hardware, but the software that manages this box, that controls the functionality of that, let's pull that out into a virtual OLT. Okay, so virtual OLT hardware abstraction is what VOLTHA stands for, right? Then let's take a further look at these other boxes. Well, maybe the pure function of moving bits around looking at IP addresses and Ethernet addresses and forwarding traffic based on those, that can be replaced with a leaf spine fabric, right? And the functionality that in software can be moved into, say, containers that run on, or VMs that run on servers, commercial off-the-shelf equipment. So leave the hardware to do the things that it's supposed to do, whether it's in the optical side or the Ethernet IP side, but the control of that hardware, let's pull that out of these specialized equipment and move it into COTS servers. So what we have done beyond that is we have said that even this hardware does not have to be specialized, right? This can be built using white boxes. So it's the use of white boxes plus pulling the control software out and moving it into white boxes and servers. So when you do this, and then you do this not just for residential subscribers, but do it for the mobile side or the business customers, that's when you get into the cord architecture. And it also then gives you the ability to introduce other services at this edge. Remember, the central office is very close to the end user, so it's the edge which gives you the ability to include other services, third-party services, per subscriber services in this architecture. Okay, so that brings me to SEBA. SEBA is basically exactly like I showed in the previous picture, right? So you have the OLT in hardware, and you have the ONU through the fiber distribution network controlled by VOLTHA, which manages the PON, and an SDN controller with applications written on top of it, which basically bring out the services that the PON gives you, okay? And that then connects to top-of-rack switches. It's a part of a fabric, a leaf spine fabric, or you can use just individual switches, one switch or two switch in an active backup mode, and that too is managed by the SDN controller. So that equipment can then connect to external routers, external BNGs, and I'll talk about that a little bit later, and also to the local compute environment where all this software is running in the compute, but it can also additionally include third-party services. Okay, what brings all of this together and into what we call a SEBA pod is that network edge mediator. Okay, so that will give you all kinds of information about the monitoring of this pod and its how it interacts with the back-end systems that every operator has, right? So every operator has different back-end systems, but they can be adapted to the SEBA pod via the network edge mediator. It's another function that the network edge mediator performs is that it talks to every other piece of software and hardware inside the SEBA pod to make sure that some functions happen before other functions, that or to take reaction to things like things going down inside the pod. So essentially there is a workflow that A must happen before B, but not if C happens instead. That kind of workflow is also different for every operator, and the NEM part of the SEBA pod manages these different workflows depending on how it is deployed. The traffic from the user, from the actual residential users, pass directly through the hardware. Okay, only control traffic, things like AAA, DHCP, and so on, they go up into the control software, but the actual data plane traffic from the end users goes directly through the hardware and out to the internet. Okay, so here's my first highlight. If you would like to know more about how SEBA, a SEBA pod can be managed by a global orchestrator such as ONAP, then it is worth going to Bora's talk in the track today at 3:30, and he will tell you about how SEBA and ONAP can potentially work together through the use of what is known as OSAM. Okay, So for the rest of my talk, as I said, I will go a little bit into explaining what VOLTHA does and what we call Trellis, which is the leaf-spine fabric to which the OLT equipment connects to. I will spend some time talking about how all this software is built on the Chord platform, which is intended for service delivery at the edge, a little bit of history about where we were, where we are now, and how things have changed drastically between in the development of Chord. We will also spend some time talking about SEBA itself, what we have built, what we are going to release at the end of the year, and a little bit about our journey of how SEBA has come together in the SEBA and VOLTHA community, and a little bit idea about the roadmap of where we see SEBA going over the next year. Okay, so let's start things off with VOLTHA, or virtual OLT hardware abstraction. Okay, so traditionally this is what an OLT would look like, right? It's a big chassis box where there are line cards, where the line cards are the PON head ends for separate PONs. So each of these over here are essentially going out to a separate PON and a separate set of end users. So you have these PON MAC blades, and then you have other compute blades for the software that is running on that box. All of these blades are tied together with a backplane, and as I said, the features that are necessary in the PON are then implemented in this. So you have a big chassis box, and when we started with VOLTHA, the idea was, okay, well, how can we disaggregate this, right? So we said that, look, the PON requires this PON MAC blades, right? So that functionality needs to stay in hardware, but the management of that hardware and also many other hardware just like that, these pizza sized boxes that are the PON head ends, okay, that management of that can be pulled out into a software stack that we call VOLTHA, which has a number of things inside it that I'll go into detail in a couple of slides. And then because VOLTHA presents this hardware to an SDN controller on top of that, that's where all the services can reside, right? And not just for one PON, but for many PONs that are being managed by collectively by VOLTHA. Okay, so VOLTHA, as I've been saying, is the virtual hardware abstraction, virtual OLT hardware abstraction. Okay, so this is a bit of a glimpse at how this all works, right? So here's a physical OLT, okay, and when we start off VOLTHA, it connects to that physical OLT and just basically says, hello, who are you and what do you have? So the OLT says, okay, these are my ports. These are my NNI ports that go upstream. These are my PON head end ports, my PON ports, and it reports all that to VOLTHA. Now, you will notice that VOLTHA then creates a logical switch abstraction, okay? But it's kind of incomplete. What it means is that, okay, here's my OLT, and these are the NNI, the uplink ports of that OLT, but there are no other ports on this side, okay? So where do those ports come from? Okay, when we discover a certain ONU, okay, and the ONU has the user-facing port, the residential subscribers-facing port, right, the UNI port. That discovered ONU in the PON also gets reported to VOLTHA, and that's when VOLTHA adds a port representing that site, right? So what then happens is, okay, that logical switch abstraction for the entire PON, right? It's not just for the OLT, but for the entire PON gets reported as a logical quasi-Ethernet switch to the SDN controller. So and as more unis get discovered on the same PON or different PONs, they then also get reported as ports on that logical switch to the SDN controller. So the SDN controller can manage these features for the PON outside the box, right? Also for multiple such boxes. Just like it would manage a real switch, right? In an SDN world, would manage a real switch with the features, bridging, routing, so on. So the idea is that VOLTHA presents an abstraction of the PON to the SDN controller, just like a switch would get presented to the SDN controller. So you can see that it is Ethernet in from the uni side and Ethernet out, and that's exactly what this logical switch has. It's Ethernet in, Ethernet out, but in between there is a lot of optical related distribution things and other things that are related to the management of the PON. There's OMCI messaging going on between the OLT and the ONU. None of that is reported to the SDN controller. So what VOLTHA does essentially is that it hides a lot of details, right? There is a lot of details in the management of a PON. If you look at the ITU standards, there's talk about TCONs and GEM ports and OMCI signaling protocol or messaging protocol between the OLT and the ONU. All of that is hidden, is not exposed to the SDN controller, which is why it's an abstraction. To the SDN controller, the entire PON just looks like a pseudo Ethernet switch that can be easily programmed, just like a real physical switch can be easily programmed, right? So this abstraction and the fact that it's a common control and management framework that is shared by all OLTs and ONUs, whether they are white box OLTs that I'll talk about a little more detail using the OpenOLT, these southbound adapters, or these are vendor ONUs and ONTs or vendor OLTs. Basically, it's this common management framework that is then further adapted by the specific device adapters for the OLTs and ONUs through these southbound adapters. Okay. So now there are a lot of exciting changes that are coming to the VOLTHA project. First of all, the VOLTHA core is being modularized, broken up into multiple containers and microservices. Already the northbound were separate microservices, and the core and the southbound adapters were previously tied together, but now they are being broken up, and the code itself is being broken up for higher performance. Also, it's moving to the Golang Go language. So if you want to learn more about these changes, please do attend Sergio's talk tomorrow at 2 o'clock. Also, there's a potential that VOLTHA can be used not just for GPON or XGS-PON based networks, but also for GE-PON based networks and G.fast based networks. So the idea is that these are all different kinds of access technologies, and while they may be doing things very similarly, they do have different differences, and they do have different terminologies, and so these differences are fed through the technology profiles, what we call different access technology profiles. These profiles will are also coming into VOLTHA. So if you want to learn more about that, I do encourage you to visit Sean's talk also tomorrow at 3:40 p.m. Okay, so now I'm going to talk a little bit about this particular southbound adapter and the use of white box OLTs. Okay, so why do I talk about white box? To me, white box is a combination of two things. Okay, open hardware specs, for example, that you will get from the Open Compute project. Okay, this box that you see over here is the industry's first XGS-PON OLT, white box XGS-PON OLT. These are open hardware specs that were submitted by AT&T to the Open Compute project. This is for XGS-PON. There is a similar one that is coming from Deutsche Telekom in the OCP for GPON based networks. So open hardware specs then lets ODM vendors like EdgeCore, for example, to put these box together using those specs according to the needs of the operator. So this is one such white box OLT that we use from EdgeCore. That's called ASF Volt 16. And then the second part of white box is the open source software. So we have VOLTHA, which is already open source, but we also have the southbound adapter in VOLTHA, which is called OpenOLT, that talks to more OpenOLT software that resides inside the box through gRPC to convey the messages from northbound all the way down to the OLT, that then talks to Broadcom software inside the box that actually manages this particular OLT. Okay, but again, this part can remain the common and there could be a different chip driver, not necessarily BAL that we use with Broadcom ASICs, but for example, if somebody comes in with an FPGA based OLT, they could write a different chip driver. Everything else remains the same. They could just write a different chip driver for their particular OLT. So OpenOLT is also software that comes from the ONF, and it basically goes back to my definition of the white box, which is open hardware specs plus open software, right? If you don't have both of these open source or open, then it's not necessarily a black box. It could be a gray box. Some people call it a bright box. Some people, and there's many of that in the industry. But this is one example where you can really buy the box from EdgeCore and get the software from open source that runs on that box. So why did we develop the OpenOLT adapter? Like I said, we wanted to ease the onboarding of different white box and even vendor equipment onto VOLTHA, right? Previously, what we had to do is that if somebody wanted to join the VOLTHA project, bring their own box to the VOLTHA project, make it VOLTHA compatible, you had to know all the way up the stack, how is the VOLTHA core behaving, how is the SDN controller behaving, then I can write my adapter which will talk to my box, okay? It's a fairly lengthy and complicated process, but what we said was, well, let's take that out of the equation, right? Let's develop this adapter that has already taken care of those things. All it has exposed is this interface, right? And as long as you manage, if you want to bring in your own box and you manage this particular interface implemented down on your chip, well, that's all you need. You don't need to worry about what is the adapter doing, how is it interacting with the core, how is VOLTHA talking to the SDN controller, and so on, right? So the number one reason why we developed the OpenOLT adapter was the ease of onboarding for new vendors. And we have seen that happen now. We did it for the EdgeCore box, but there have been other vendors, some white box, some not, who have either used OpenOLT directly or have inherited from OpenOLT, right? And we have seen the same thing happen with the ONU adapters, what we call the OpenOMCI ONU adapters, and there are a number of ONUs that also use that same adapter. Okay, so if you want to learn more about OpenOLT, I encourage you to visit Shad's talk tomorrow at 2:55, and Chip's talk about OpenOMCI ONU adapters and the whole OpenOMCI library that has come in to VOLTHA also tomorrow at 3:20 p.m. Okay, so that's all I wanted to talk about VOLTHA, just give a very high level overview of the key points, and now I'm going to shift my attention to, okay, once you're past the OLT, once you've gone from the residential user, gone through your ONU, gone through your OLT, what do you hit next? Well, what you hit next is Trellis, right? In the exemplar implementation of SEBA, we do use Trellis as a multipurpose leaf spine fabric. In its full glory, it is in fact a multipurpose leaf spine fabric. However, I should caution you that SEBA uses the smallest instantiation of Trellis, okay, a single switch. So I will tell you a little bit more about what Trellis does in its full glory, but you should remember that in SEBA, only the smallest instantiation, a single switch, is used today, and in the future we have plans to use two, a dual TOR combination with active backup for high availability. Okay, so this is what SEBA looks like. This is what Trellis looks like, and in its full glory, what I've said is that, okay, here's two top of rack switches that are paired. We call these paired leaf switches. You can have more of these pairs. You can connect it to spines. Those spines themselves can connect to other spines in different locations. So for example, this could be the primary central office, the primary head end, and this could be a number of field offices, secondary head ends, secondary central offices that all connect to the same primary. So the fact is that you could have the compute infrastructure in the primary location and no compute in the secondary location, just the access equipment in the secondary locations, and then that traffic then connects to these spines in the secondary location. They then forward it to the spines in the primary location, and then reach either the compute infrastructure or the upstream network, right? So Trellis in its full glory does look like this. It's a multi-purpose leaf spine fabric, which I say is designed for NFV, because unlike many other leaf spine fabrics that you find in the industry today, they're really meant for data center operations. They're probably just IP fabrics, but as we know with telecom operators, they deal with lots of different kinds of traffic. So mobile stuff can be coming over GTP tunnels, and residential stuff can be coming with Q&Q VLANs. So your fabric has to deal with all of these different kinds of traffic and provide different kinds of services. So that's why I said Trellis is multi-purpose, and it's designed for NFV. It's also important to note that Trellis is also built with bare metal hardware that comes from the Open Compute project. So just like the OLT equipment that I showed in a couple of slides before was built on bare metal hardware with open specs and open source software, Trellis is similar. It is also built with merchant silicon, white boxes, open source software, and just like VOLTHA, it is also managed in an SDN way through an SDN controller. We use ONOS. Okay, so Trellis, as I said, supports a number of features: bridging, routing, multicast, unicast, V4, V6 that you would normally find in traditional commercial leaf spine fabrics from multiple vendors. But in addition to that, it does a few things that you would normally not find in such products. And today Trellis is supported on ASICs from a number of different ASICs from Broadcom, and it has some preliminary support for a few other ASICs from different vendors like Cavium and Barefoot Tofino switches. Okay, so this is what it looks like. That's your hardware, and this is all Broadcom ASICs inside EdgeCore and also other ODM vendors like Delta. But the software that runs inside these boxes is exactly the same. It doesn't matter if it's a leaf or a spine switch. The speeds and feeds are different, right? But the software that runs inside the box is the same. And so what do we use? We use software that comes from the Open Compute project. So ONL as the base Linux running on the box with a number of drivers, ONI as the bootloader, and then we use software that comes from Broadcom. It's called OFDPA, or Open Flow Data Path Abstraction, that just like VOLTHA presents a picture of the hardware to the SDN controller. Okay, so if you remember, VOLTHA presents a picture of the PON to the SDN controller, and what OFDPA does is that it gives you a picture of the pipeline inside the switch to the SDN controller. So if you're familiar with the ASICs that Trellis supports, you can understand that there could be a number of different kinds of pipelines. The pipelines under the hood could be actually very different. But what OFDPA does is that, don't worry about it. We've taken care of the differences between these different ASICs, but we have presented this picture to the SDN controller, so the SDN controller knows what it wants to program, whether it's the bridging tables or the routing tables or MPLS or VLANs. Do you want to do ECMP groups, multicast groups, whatever be the case, right? We have that ability to program these tables, and then under the hood OFDPA matches those tables to what the actual pipeline is inside these different ASICs. So Trellis today looks like this, right? So you have your SDN controller with the services running on top. Again, very similar to the VOLTHA case where you have the SDN controller running with services on the top, and then managing the pipeline that is exposed on these ASICs in a leaf spine fabric configuration to bring out all the features that I had shown a couple of slides earlier. Now we have done a few other things with this. What we have done is that, okay, the pipeline that is given to us comes from OFTPA. But what if we want to make some changes to the pipeline? And that's where P4 comes in, right? So there is P4 capable hardware that can be programmed. You can actually make changes to the pipeline for a particular purpose, right? So we have in the past shown, now this will have a different driver than what we use over here, and in the past we have shown that, okay, I can write a P4 program that does the things that Trellis expects and normally does, bridging, routing, and so on. But in addition to that, I can have the ability, for example, to implement a functionality that is needed for an SNP gateway. So I need to be able to, say, encapsulate and decapsulate GTP tunnels that is coming from mobile subscribers, right? So that may not be a capability that is supported in these ASICs, but the programmable ASICs, I can actually create a pipeline that does that encap decap, and that functionality is driven in a different way through different interfaces into the box. So Trellis today is compatible with both, right? It can use these interfaces to work on this set of ASICs, as well as P4 to work on a different set of ASICs. And that brings up the ability, and it's the same application. The ONOS is written in a way where the applications don't have to worry about the differences in the pipelines. The applications are written one time, and then they are adapted through these drivers to work with different ASICs and different abstractions, different pipelines. Okay, so that brings up very exciting possibilities in the future about how we can take Trellis and introduce newer features that are needed for the operators and the central office traffic that the central office sees. Okay, so there's a couple of talks that I did want to highlight. There's Carmelo's talk about how we have introduced P4, especially the fabric.p4 program that Trellis uses to work with this newer hardware. So his talk is in the ONOS track on Thursday at 3 o'clock. There's also Charles's talk that gives you a lot more detail about how Trellis, the internals of Trellis and how it works. So that's on Tuesday at 4:30. Okay, so that's all I want to talk about Trellis. Now let's move on to Chord. Okay, Chord has a history of the last 2 or 3 years, and we had tried to deploy Chord in a number of service providers networks, but we ran into a number of different issues. Okay, and those issues are actually kind of highlighted in this particular slide. There were many things. A lot of the software was built from source at deploy time. There were maybe big scripts, huge scripts, scripts calling other scripts. It was a long process, and it was a little bit brittle, right? If something broke, then you had to start from all over again. There was a way to start from the step that broke, but only if you knew exactly what to do and what files to move around to start from step 3 instead of step 1 and so on. So and small variations of the pod that we were trying to deploy, if there were, it could cause these scripts to break. So it was hard to deploy. It was also not exactly very modular, right? There were tightly coupled components, and we were requiring certain specific versions of the OS that was installed in the equipment, and that also led to problems. For example, we went and said, we need this particular version of say Ubuntu to install for this pod, and the operator would say, well, no, there's no way we are going to do that. We have our own version of Ubuntu that we are we have made secure and so on, and we trust. So we're just not going to take what is upstream and put it on our equipment. So that was a problem. So we learned a lot over the last 2 years in trying to do these deployments. And basic message was that yes, it's hard to develop on, it's hard to deploy, it's hard to run it at runtime. So we took all these messages, right? We understood, we went back and rethought how we would do it. And I'm happy to say that around July, so middle of this year, we came up with the 6.0 version of the CORD platform that completely changed, and all of our learnings were put into this. So today, if you use the CORD control software, it's basically a set of Docker containers that run on Kubernetes and use standard tools like Helm charts for installation, right? So what we have said is that, look, okay, go ahead, right? If you want to use your own secure version of Ubuntu, go ahead and do that. We don't care, okay? If you want to use a specific version of Kubernetes that you want to use, as long as our software will work on that version, we don't really care. You deploy it, you install it whichever way you want. We are not going to prescribe it, okay? And on top of that, that's where we come in. Once you have this installed base, right, on top of that, you can install the pieces of the CORD platform and the profiles that we need, like SEBA, on top of it. So for example, you can say that if the Acreno project has a way of installing the operating system and the Kubernetes and all of that is being handled by the Acreno project, SEBA can essentially be a blueprint that runs on top of Acreno, and this is what happens, right? So we install the CORD platform, so it's ONOS, it's XOS, and it's Kafka, plus a number of monitoring software that we use like Prometheus, Grafana, the Elk Stack, and so on. Right? Once you have the basic CORD platform installed, that's when you install a profile on top of the CORD platform. As I said before, SEBA is a profile that runs on the CORD platform, and so if you want to understand more about how all of these changes, a bit of the history of where we have gone through and what we arrived at, I do encourage you to visit Luca's talk in the CORD track on Wednesday at 2 o'clock. And like I said before, SEBA is essentially a profile that runs on top of the CORD platform, right? So it involves the software that is needed to control the PON, so that's VOLTHA. It's got a collection of ONOS applications and XOS services, and finally it's got a workflow essentially being a state machine to manage and orchestrate what happens before something else happens, right? And so every operator has essentially a different workflow, and I'll come to that in a bit. Okay, so all the runtime configuration and service instantiation happens on top of the profile. All right, so if you want to know more about that, I also encourage you to visit Mateo's talk in the CORD track Thursday at 3:30 p.m. Okay. You would have also heard of RCORD in the well. So on top of the CORD platform, we had a profile in the past that we called RCORD, and RCORD used to do things differently. So the traffic that comes from the residential subscribers goes through the hardware OLT as well as the switch, but then it used to go into the compute nodes to through a virtual switch like OVS, and then visit a container that is called the VSG, or the Virtual Subscriber Gateway, what we used to call it, right? And that traffic from the VSG could then go back out through the hardware to the internet, or it could go through a number of third-party services, for example, a CDN service, right? So this was the basis behind RCORD. It had a number of other differences also. You know, the head node used to be different from the compute nodes. That was more a platform thing. But what we have done in SEBA is that we no longer have data plane traffic going to the x86, going to the compute nodes. Now the traffic, the data plane traffic for a particular subscriber just goes through the hardware out into the internet, and only if we want to provide a certain third-party services for certain subscribers, or a subset of the traffic for certain subscribers, that's when we leave the hardware to go into the compute nodes and possibly to containers for that particular service. So the common case, right? The common case of getting high-speed internet access or IPTV access, all of that happens through the hardware now, and it's only in the, you know, if you've taken care of the 90%, but in the 10% cases where we do need to provide a certain service closer to the end user at the edge essentially, that's where we come out of the hardware. So that's a major difference between what we do in SEBA, what we used to do in ARCOD. Okay, so putting it all together, this is the things that I've been telling you about. I've been telling you about VOLTHA and how we use an SDN controller for services to manage the PON, how we use an SDN controller to manage the aggregation switches, which is the smallest instantiation of Trellis, how the traffic goes stays in hardware and only if necessary comes out, the data plane traffic that is, and all this control plane software is managed as containers that are running on these compute nodes and managed using Kubernetes. And now the piece that I haven't told you about is the NEM, as the network edge mediator that provides all the FCAPS functionality, the inventory, and the mediation with the outside world, outside the SEBA pod, being the operator's backend software. Okay, so different operators, like I said, have different workflows. So examples of that could be that, for example, AT&T might want to do 802.1x based authentication of residential gateways that are sitting behind these ONUs, but Turk Telecom might want a PPPoE based authentication, and some other operator might just be happy with DHCP based authentication. Okay, other examples are all these services that are presented to the end user. There may be differences in how these services are presented to the end user by different operators. That's also part of the workflow. This BNG that this traffic actually terminates at before it goes out to the internet, that BNG might be an external hardware, could be also virtual BNG that is running in the compute, or it might be that the functionality can actually be implemented in the hardware, either in the OLT or in the aggregation switches, which is actually on the roadmap for SEBA. So BNG is also a workflow option, right? You have all these choices. So different operators, different workflows. Workflows are implemented in NEM. Okay, that is the one, that piece that touches all the hardware and all the software that is running inside the SEBA pod, and therefore plays this orchestration role for different operators according to where it's deployed and how the operator wants certain things to happen. Okay, so if you want to learn more about NEM and this workflows and this operation of how it looks like internally, please visit Scott's talk in the core track at Wednesday, that's tomorrow at 3 p.m. There's also another piece of NEM, which is the monitoring infrastructure, right? So here we use a number of different third-party software that we add to. There's the LStack, which is Elasticsearch, Logstash, and Kibana. We also use a time series database like Prometheus, and then display that using Grafana. All of that is fed through a Kafka stack, which VOLTHA also uses. VOLTHA and ONOS both use to feed information, as well as XOS feed information. So, and also there's a number of statistics that we can get from the hardware, whether it's PON level statistics or it's statistics from the fabric switch, the AG switch. All of that is fed either from VOLTHA or ONOS on the Kafka bus and then gets into Grafana. As I've said before, logs can go again from VOLTHA, from ONOS, from XOS through the ELK stack and be searched in Kibana. We can also get information from the compute nodes as well as the hardware, other different kinds of information using Redfish APIs. That too can be fed into the NEM monitoring infrastructure. And it's an optional part of the piece because you may use this in the pod. Because everything shows up on Kafka, that can actually be fed outside to the operator's OSS as well, because the operator in a particular instance might want to use their own monitoring infrastructure, not necessarily the one that comes in the SEBA pod. So to learn more about this, Zach is going to talk more about this on Thursday at 3 o'clock in the core track. So that's a really good talk to go to as well. So a quick look at what these dashboards look like, this is something that you will see from the XOS GUI. For example, this is the user interface that tells you about the inventory, the service instantiation, workflow status. So in this particular case, you're looking at AT&T's workflow for the SEBA pod, and it's telling you things about how authentication is being done, what is the DHCP assigned IP address, what is the state of the ONUs, are they enabled, are they disabled, and so on, right? So this is one dashboard. And then the monitoring, of course, this is showing you the Grafana dashboard for statistics that we're getting from the PON, and then there are, there's other dashboards like Kibana as well for looking at various logs vertically through the stack. So we've done a recent demonstration of this at the Broadband World Forum in Berlin in October. And in that one, we had the SEBA pod with a number of different equipment from OLT and ONU manufacturers. And we even had this BBSIM, which is a simulator for the PON that simulates this control traffic. So it's really, this is what the pod actually looked like. Here's your servers running all of the core SEBA software. Is the aggregation switch, the Trellis aggregation switch is just one switch to which all of these OLTs are connected through the fiber distribution network, and then finally the ONUs. Okay, so so now let me tell you a little bit about the development of SEBA and its roadmap. SEBA was primarily developed by ONF, working very closely with the AT&T Foundry and the larger groups in AT&T who have helped us understand the needs of what a disaggregated PON system should support. So we have worked very closely end to end, and then there are a number of companies that form the community, right? Mostly this is the VOLTHA community, which is a very strong community with a number of folks that contribute greatly. So you can, for example, the second version of VOLTHA comes from Sienna that you can hear in Sergio's talk, different OLT and ONU vendors, Radisys, Netsia bringing in the technology profiles that you can hear in Sean Misset's talk. We have test automation and certification that you will hear about from Siddharth from Flex. And then you have contributions that come in from Adtran, for example, the OpenOMCI spec, and Broadcom, which is the software that runs on the white box OLT. So it's a very rich and vibrant community, the VOLTHA plus SEBA community that has built this together over the last year. ONF itself has a number of different responsibilities. Of course, it's this joint development that we work very closely with the AT&T Foundry, daily scrums, bugs, design discussions, and so on. We also, of course, support the VOLTHA and SEBA communities through mailing lists, and we have regular meetings about JIRA issues and so on. So there's a lot that goes into supporting the community and driving the community and helping the community thrive. We ourselves have an engineering team that delivers a number of different features, whether they are on the SDN controller, whether they're in the NEM piece, or even the VOLTHA piece. We work a lot on ensuring the stability of our software, and we investigate the scalability and the performance of a full SEBA pod and ensure that we scale. We are on the path to ensuring that it scales. We develop tooling. So for example, you can't measure the scale of a SEBA system unless you develop a tool that is able to simulate thousands of subscribers. So we are doing the work to do, it's called BBSIM, and it's a tool that will help us scale the SEBA pod. If you don't have the hardware but you want to get involved with SEBA, then SEBA in a box is another tool that we have developed that will let you run a SEBA pod with emulated hardware for both the PON hardware as well as the switching hardware. And finally, we do a lot of QA development with our partners like Flex and Northforge and so on. So this is all the things that ONF is responsible for. If you'd like to learn more about SEBA in a box, I highly encourage you to visit Andy's talk in the SEBA track tomorrow at 5 o'clock. If you'd like to learn about how we do QA, again, Siddharth from Flex is going to talk about it tomorrow at 5:30. Okay. Here's a picture that quickly talks about the deployment of SEBA and what it will look like physically at AT&T. This is our goal. They actually have this running, as you have heard in the plenary earlier today. They have this live in the field with 120, with the capability to reach 120 subscribers. Okay, so I did want to spend a couple of minutes talking about the modularity in SEBA. Now, over the course of this talk, you've heard me talk about the hardware, of course, and all of these software. Think of it as, you know, Lego pieces that have, or Tetris or something. But I have stacked them up over here in a specific way to give you an idea about how modular SEBA is designed to be. Okay, so first box that I will draw is around the PON hardware that is managed by VOLTHA and SDN controller like ONOS and the applications that run on it. Okay, so I don't know any other substitute for VOLTHA, and VOLTHA is very unique. But VOLTHA is also, should be recognized, is not a standalone piece of software. It is meant to be used with an SDN controller like ONOS and have the applications running on top of it, right? So similarly, Trellis is another box that you can imagine. It's the aggregation switch, the operating system that runs on it, that is managed again by an SDN controller, and the applications that bring out the services in the hardware. Switching hardware. Finally, we do have another box that we can draw around the compute nodes and the use of Kubernetes, Kafka, and so on. Like I said, both ONOS and VOLTHA and pieces of NEM are in fact our monitoring infrastructure is based on Kafka. So this is another piece that you need. But you know, I'm drawing another box around the applications that run on top of the SDN controller. We're often asked, hey, can I substitute your choice of the SDN controller with another choice? And I say, yes, that's fine, that's possible, but you have to ensure that these applications then are also written on top of the SDN controller, because if you're familiar with SDN controllers, applications are typically not portable across controllers, right? So if you want to switch out, say, ONOS from a SEBA pod and put in a different SDN controller, you have to ensure that the applications that are running on top of it are also ported onto that particular controller and its APIs. Okay, so similarly, if you want to swap out the switching hardware, for example, right, with some other SDN based switching hardware, or even non-SDN traditional switching hardware with all the software running inside the box, that's also possible, as long as you ensure that the hardware, it meets the hardware requirements for what it connects to, as well as the software requirements of what it's driven by. Okay, so yes, these pieces are modular and can be replaced as long as you ensure that the APIs into that modular box are satisfied. Okay, another piece is what we call the NEM. The NEM piece, you know, I've put a box around what we are using here, XOS. Again, there is a, if you want to replace it with your own orchestrator, that's completely fine, as long as you ensure that that orchestrator can reach all these other pieces of hardware and software that we use inside the SEBA pod, and implement the workflow, for example, that we use for a certain operator, right? And the NEM piece, the monitoring piece, I've also said that you don't, it's optional, you don't necessarily need to use it. You can take things that are put on the Kafka bus and take them directly, for example, to the operator's backend and have your own monitoring software in there. Okay, Abstract OLT is a piece of software that is meant for interacting with a global a global orchestrator like ONAP. Abstract OLT is, the best way to think about it is a view of a SEBA pod, a specific view of the SEBA pod presented to the global controller for managing the SEBA pod, right. So if you take all of this, the SEBA pod, but make it look like the chassis OLT, a traditional chassis OLT, okay, that is one view of the pod that is presented to the global orchestrator. So just like the global orchestrator used to say manage a traditional chassis based OLT, it can similarly manage a SEBA pod via the view that is presented to it by this piece of software that comes from AT&T called Abstract OLT. So you may use it if you want to use say ONAP, but a different operator can make a different choice. If they don't want that particular view of the SEBA pod, that's fine. We don't have to use Abstract OLT. If you don't want to use a global orchestrator like ONAP, that's fine as well, right. So this can hopefully give you a little bit of a flavor of the modularity that exists inside and outside the SEBA pod. So my last slide, I wanted to talk very quickly about the roadmap. We do want to, so right now in the SEBA pod, the BNG is outside the pod. It's an external BNG. That's the first choice we have made. There are choices of using a VBNG. There's also choices of using disaggregating the BNG and having that functionality be implemented in the OLT and the aggregation, the fabric switches. So that is a talk that comes from Hans-Jörg tomorrow, actually at 3 o'clock today, tomorrow, that I encourage you to visit to learn more about how Deutsche Telekom has done BNG disaggregation. We do want to leverage P4 like I've shown in Trellis for the aggregation switch to bring in new functionality in there. We have the AT&T workflow today, but we also have Turk Telecom giving us their workflow, and we are talking to them right now. So we do want to install more workflows, and of course there are performance and scale improvements that are necessary for production scale and for trials. There are a few parts of the SEBA pod that are not redundant, and we want to bring in that redundancy. For example, we use a single switch of Trellis as the aggregation switch for a number of OLTs. So if that switch dies, we have no failover. So we do want to expand that into 2 switches that can do active backup failover, and there are a few other examples of that. Like I said, there are new things that are coming into VOLTHA. Technology profiles, a new Golang based core. Those are things that we have to integrate in the near future. In-service software upgrades is of course always important, and things like bringing in other profiles, sort of. So there are people who talk about base station communication in the mobile world, base station communication to an EPC that is sitting inside a CORD environment, and that communication can actually happen over a PON. So in principle it's happening over SEBA, right. So if you take the MCORD profile and use the SEBA as for transporting that communication, that's something that we are also very interested in looking at. So to summarize, ONF, as you know, is an operator driven and curated open source, and CORD is our flagship umbrella project, and SEBA is an exemplar implementation that is built on top of the CORD platform, right. It has a number of modular components. VOLTHA, that is meant for making the PON look like a switch to an SDN controller. Trellis, that manages a real switch in an SDN way. It's multi-purpose and built for NFV. ONOS is the SDN controller that manages both VOLTHA and Trellis. XOS is something that we use for service delivery and orchestration of workflows. Add that to all the pieces that we use for monitoring, and together we collectively call that the network edge mediator, or NEM. And CORD platform itself has gone through a lot of changes. It is now a set of Docker containers that are managed by Kubernetes. So SEBA, as I said, is a profile that is instantiated on CORD. It's jointly developed by ONF, AT&T, and the large VOLTHA community. and we have now put in a significant focus on the FCAPS infrastructure that is necessary for operators to manage these PONs. So you've seen that through the work that we have done in NEM, and also can support multiple operator workflows, not just what AT&T wants in from a SEBA pod, but what Turk Telecom could, for example, want in a SEBA pod. It's the same components, just behaving slightly differently or in different order, right? So multiple workflows. It is headed to trials at AT&T. In fact, it is already in trials, and there is significant interest from operators worldwide. Okay, thank you very much.